Okay, so today's discussion over the first two periods of review are compare and contrast questions. This is kind of more the paper two type of question, where it's a 2 or 3 mark question where you're comparing or contrasting different ideas, and you're talking about like the differences, but also the similarities between them. And there are a few different topics. I've listed a few of these. Some of them at the end are kind of a stretch, but a lot of these things are ones where you're comparing two ideas and making sure that you really understand them, because um, even for multiple choice questions, there are a lot of times where the IB will use this opportunity to kind of differentiate between things to make sure that you recognize the differences and things like that. But so the first one we'll talk about is voltaic versus electrolytic cells. This is a very common one for multiple choice and for short answer. And so when you're looking at voltaic, I'm trying to figure out how I want to do this. Okay. 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 Similarities will be in the middle. The differences will be on the other side. So first and foremost, things that are similar but or identical between voltaic and electrolytic. Okay. One, the anode is always oxidation. Regardless of which cell you're dealing with, it is oxidation. And the cathode is reduction. That is a guarantee for both types of cells. So don't let that kind of trip you up and assume that they have to be opposites, because they're different functionalities. Electrons flow, from the anode to the cathode. So no matter what, whether it's electrolytic or voltaic, the electrons are still flowing from the anode to the cathode. Okay. You have two electrodes. Okay, in both voltaic and electrolytic, you have two electrodes. Okay, you also have an electrolyte or electrolytes, depending on which type of cell you have, but you do have something that's conductive, a conductive solution, or a conductive, I guess we'll say solution or liquid, depending on if you're talking about molten and things like that. Okay, so you will have an electrolyte or electrolyte. Let's see. I'm getting a little nitpicky here, but you will have a wire that conducts electricity from the anode to the cathode as well. Let's see, is there anything else? Those are the main ideas, the similarities here. Okay. Now the difference is, for the voltaic, you have a negative anode and a positive cathode charge. So the charges of the respective electrodes does differ in electrolytic versus analytic. Voltaic. I don't know if I said analytic. So the charges are the opposite. The way I think about it is, in electrolytic, because it's a non-spontaneous reaction, the anode to oxidize, you have to attract the species that want to oxidize, that want to lose electrons, and those species are generally negatively charged. So the only way you're going to attract those to the anode to cause them to oxidize is if you have a positive charge on the anode. Whereas the voltaic, the oxidation happens naturally, spontaneously, so therefore the density of electrons will be at the anode, and then it'll move across the cathode spontaneously. So the difference in charge is one big thing of the anode and the cathode. Okay. Second thing, a voltaic cell is spontaneous. Means that it generates current. So the voltaic cell is essentially like a battery. It produces electricity through its chemical reaction. Whereas an electrolytic requires a power source to force the oxidation and the reduction to happen. Okay. For higher level, voltaic cells have a positive cell potential, whereas electrolytics have a negative cell potential. I kind of want to say 2 cells versus 1 cell, but I've seen questions on the IB where they have a voltaic cell in a lemon, which is just really 1 cell. And so I don't want to kind of ingrain in your mind that like a voltaic cell always has to have 2 cells. The main idea of voltaic cell is it has to be spontaneous, it has to generate electricity. And so through the oxidation and reduction of the species there. Okay. I guess the only other thing that you would say for voltaic is it might need a salt bridge to maintain charge in separate cells. So if the cells are separate, like we usually diagram in our notes, then there is a salt bridge that's required to maintain the charge in separate cells, because the salt's ions go toward the solutions to reduce the charge in each solution. Okay. So a lot of similarities. Where I think the IB tries to trick you is they'll either ask like what's being produced on the anode, what's being produced on the cathode, or they'll say what's being produced on the positive electrode and what's being produced on the negative electrode. So understanding those differences there is where it gets kind of challenging and where it's kind of tricky, because if you forget the charges, then you'll get the wrong products being produced. But so you need to remember the charges are the opposite, but the actual reaction that happens on each electrode is the exact same. So they might ask like, compare the products being produced on a voltaic cell and electrolytic cell, or compare the half reactions occurring at the following electrodes in a voltaic versus electrolytic, and both the voltaic and electrolytic both have oxidation on the anode and both have reduction on the cathode. Now, if they ask you about the charge of the electrodes, then a voltaic, the negative electrode would be oxidation, and the positive electrode for electrolytic would be oxidation. So that little kind of detail here is that really kind of next stage of thinking and application of these ideas. So really be cognizant of that. Okay. Questions about that? Make sure everyone's got it written down. Okay. Strong versus weak. Now, I'm going to stick with acids here, because in acids, you see the properties of strong and weak electrolytes, but you also see other characteristics that you want to address. And so we will address that kind of in this similar table as well. Okay. Okay. So strong acids versus weak acids. So similarities. Okay. One, react with reactive metals to form H2 gas, and a salt. Okay, so whether you're a strong acid or a weak acid, you react with similar things. You can react with carbonates or hydrogen carbonates to produce CO2 and water and a salt. You can react with a base to form salt and water. And the pH will be less than 7 at 25 degrees Celsius. For a higher level, that matters because the neutral pH can fluctuate based on temperature. So it may have to be less than 6.5 at higher temperatures or less than 7.5 at lower temperatures. So that does vary, but I do want to have a general idea here, okay? They both produce H plus ions in water. They both can conduct electricity. Where a lot of things differ is to what extent, right? Because that's the real difference between weak acids and strong acids is to what extent do these reactions and these characteristics are represented in these solutions. And let me make a note up here. Let's assume they're equimolar or same molarity. That makes things a little bit easier for us to compare and contrast. So let's assume that we have the same molarity of strong acid and the same molarity of weak acid here. That'll make the list a little bit easier to write. So with these reactions here, strong acid will react more vigorously or violently or faster. Whereas the weak acid will react more slowly. Oh, let me add one more thing to the similarity. Okay, same amount of product is produced whether it's a strong acid or a weak acid. It just takes longer time. So I guess we're assuming that it's like some monoprotic acid, like we'll just say HA. So we're not going to like involve sulfuric acid, which is H2SO4. We're just going to compare like two monoprotic acids. Because if you have sulfuric acid versus a monoprotic, then yeah, you'll have different amounts of product produced, but you should have the same amount of product produced in both of those. The pH will be lower in your strong acid due to the 100% dissociation versus the partial dissociation, which is usually less than like 1%. So if you compare the pHs of both solutions, the strong acid should have a lower pH. Now, usually the IB doesn't let you use pH as a differentiation because it's too obvious. So they'll say, excluding pH, state one method of identifying which acid is which. And so one would be reactions, and also the other one would be conductivity. So because of the dissociated ions, you will have a greater conductivity because there's 4 free-moving ions that are present in the solution. Now, higher level thing, a strong acid plus a weak base makes an acidic salt. With a strong base makes a neutral salt. And that has to do with your equivalence point. Whereas a weak acid plus a strong base makes a basic salt, and a weak acid plus a weak base depends. Versus the Ka versus Kb of each thing. Whichever one's greater, that's the one that dictates whether it's going to be a basic or acidic or neutral salt. If the Ka and the Kb are the same, then it'll be a neutral. If Ka is greater, then it'll be acidic. If Kb is greater, then it's going to be basic.
Mr. Chong, do you mean weak base on that second?
Oh, yes, sorry. Yes, you're right. I just looked at it. Yeah. Weak base. Thank you. Also, for higher level, can be 1 part of a buffer solution. With its conjugate base can form a buffer solution. Okay. Now, strong acids can help form buffer solutions, but they themselves can't be buffer solutions. They have to react with a weak base to form. Oh, yes, Alexander. Sure. If for some reason they have a weak base plus a weak acid, and you're trying to figure out what kind of salt it'll be, you look at the Ka of the weak acid and the Kb of the weak base. Whichever value is larger, that will determine whether your salt is acidic or basic. That's a very niche thing. I'm not exactly sure, but knowing the IB, they'd find a way to incorporate it into like a 1 mark or 2 mark question, right? So, yeah, I'd be careful about that. Other questions about this chart? Okay. Let's scroll up here. Okay, so we've done this, we've done this. Okay. Some of these charts won't be as like extensive. For example, this K versus Q one. I'm not gonna draw the lines yet because I'm not actually sure how long this is gonna be. Okay. Similarities for K versus Q, capital K versus capital Q. Both are expressed as products over reactants. Now, obviously, if they give you a reaction, your expression actually involves your species, but you calculate K and Q the same way. Okay. They're both related to equilibrium, in a manner of speaking. Okay. Now, the thing is this, K is the equilibrium constant. So that is already at equilibrium. Whereas Q is called the reaction quotient. Which is at non-equilibrium conditions. So your job using Q is to figure out, okay, which way do I have to shift to reach equilibrium? So whereas when you look at K and you say K is greater than 1 or K is less than 1, K is greater than 1 favors products and K is less than 1 favors reactants. For Q, you're not comparing to 1, you're comparing to K. Q is either equal to K, less than K, or greater than K. So there is a difference in how you compare those two ideas. If Q is less than K, that means the value of Q is smaller, which means that you have too much reactants, because reactants are on the denominator. So if you have too much reactants, it has to shift to the products. So the position of the equilibrium will shift to the products. If Q is greater than K, that means your value of Q is too large, which means you have to lower it, which means you have to make more reactants. So it'll shift to the reactants. Yeah. And again, if you have trouble visualizing this, I make up numbers. Like I'll just say Q, for example, is 3/2, and then K is, see, 1/3. Okay. The idea here is this value is smaller than this value. And the only way that I can make this value larger is if I make my numerator higher and my denominator lower. Sorry, backwards. Wait a minute, I'm saying this wrong. Oh, sorry. I wrote the fractions the opposite way of what I was trying to do there. My fault. Okay. Let's just do it like this, 9/2. Sorry. I drew the arrow and I had a different idea. So here, your Q is smaller than your K. So therefore, you have to make more products to raise the value of the fraction. So your reactants will decrease and your products will increase, hence getting a larger number. So if you have trouble visualizing it, just write numbers out and go, okay, what do I have to do to make this number larger? Well, I have to make more numerator by taking away denominator. So it's going to shift toward the products. If Q is equal to K, then you're at equilibrium. This is I would say this is more of a multiple choice kind of question, where they give you the K value and maybe give you the concentrations of the reactants and products at a given situation, then ask you to identify which way it has to shift to reach equilibrium. And so that's where you're applying this concept of K, capital K versus Q in this. Okay. Or like maybe they'll just say, discuss the statement like when Q is less than 1, the reaction favors the reactants. Well, there's a lot of problems wrong with that statement because Q is not related to 1. Q has to be related to the equilibrium constant. So Q less than 1 has no bearing on whether the reaction favors the products or favors the reactants at equilibrium. So, like, if I were trying to ask kind of a tricky question, that's what I would ask. And then there'd be students that just think about less than 1 as favoring reactants, and they don't understand that Q is actually not at equilibrium yet. So the fact that it's less than 1 or greater than 1 has no bearing on whether it favors the reactants or products because you haven't reached equilibrium yet. K might be 1,000, but Q is less than 1 just means that it still favors the products. Questions about this? And this is all standard level as well. Q and K, those are standard level concepts. So that's for everyone. Okay. Oops. Endothermic versus exothermic. Okay. Comparing these two ideas. Now, I don't think the IB will have you state and explain or compare and contrast these two ideas, but differentiating between these ideas is really important for you to apply in a lot of different situations, whether it's Le Chatelier's principle, whether it's Hess's law, whether it's equilibrium, or whether it's like stoichiometry of calculating how much energy is produced or used, or phase changes and things like that. These ideas do contrast each other, and so it's important that you are able to identify the differences between these ideas. Okay. Now, endothermic, in that process, heat is absorbed from the surroundings. Whereas in exothermic, heat is released to the surroundings. Okay, that's the kind of most fundamental idea or concept of this. Okay. If we were to draw the reaction energy diagram, it would look like this: the reactants and products. And that would be your delta H. Versus this being your exothermic reaction, where that would be your delta H. Which means that this will have a positive delta H value for the overall reaction. This will have a negative delta H value for the overall reaction. Which then means that when you're incorporating this into an equation, you no longer need the positive and negative sign. You just need a positive sign, but the location in the reaction is where it differentiates. And so this would be A plus delta H yields B versus A yields B plus, delta H in this reaction. I guess let me try to draw these lines here. Oh, it's gonna really be annoying. What that also tells us is reactants have lower energy than the products. So that means the reactants are more stable. Anytime a species or an atom or a molecule is at lower energy state, it is more stable because species always seek to be in the lowest energy state possible. Whereas here, products have lower energy. So products are more stable. And if I'm trying to minimize what I have to memorize, I find that this graph here, this reaction energy diagram, is very useful in thinking about all of these different ideas here, right? Because you think about what's more stable, the reactants or the products, where your delta H is. And so to get from reactants to products, you have to add heat. To get from the reactants to products, you have to subtract heat. I think that reaction energy diagram will help you visualize a lot of different things without having to memorize every single row of this compare and contrast. Okay. Phase changes. Going from a solid to a liquid to gas is endothermic because you have to absorb energy to break the intermolecular forces. And I say intermolecular forces very explicitly here. Don't ever say the word bonds when you're doing phase change because that shows a lack of understanding of what's actually happening. And you can actually invalidate the rest of your answer by just saying bonds because you've essentially shown that you don't understand what's actually happening because you're misspeaking. So it's always IMFs. Whereas the reverse reactions are exothermic because to crystallize or to condense, the particles have to lose energy so that they slow down and that the intermolecular forces of attraction can resume and then start to change the state of matter at that temperature. Endothermic is bonds breaking, and endothermic is bonds forming, okay? So that relates to bond enthalpy. So that relates to understanding what the sign of bond enthalpy will be on the reactant side and on the product side, okay? On the reactant side, you're breaking all the bonds. On the product side, you're making all the bonds. So when you make bonds, you release energy. When you break bonds, you absorb energy. So therefore, your reactants should be positive and your products should be negative in bond enthalpy calculations. So keep that in mind. Okay. Now, there are some similarities. Okay. They both relate to enthalpy. So heat change, wow, those are really slanted lines. I think this is a fruitless endeavor here. Okay. They both have to relate things to like enthalpy of combustion, enthalpy of formation, Hess's law, calorimetry, and bond enthalpy. Okay. Let's see. For higher level, you're going to relate this to delta G in the form of delta G is equal to T delta S. So no matter whether endothermic or exothermic, you're going to relate that value to your delta G or spontaneity calculations. And it'll help you determine whether the reaction is spontaneous or non-spontaneous. They'll both have a temperature change. Now again, with the endothermic, the temperature change will decrease. The temperature will decrease, whereas in exothermic, the temperature will increase because this is always of the surroundings. So whenever you measure temperature, you need to remember that your temperature measurement is always of the surroundings, not of the actual reaction. That's impossible because your thermometer by default is part of the surroundings. So it's absorbing the energy that the reaction is releasing, or it's losing energy to the reaction so that the reaction can absorb it. So there will always be a temperature change, but that's always of the surroundings. So when you do calorimetry, if your thermometer goes up in temperature, that means your water is absorbing more energy, therefore your reaction is exothermic. But if your temperature decreases, then your reaction is actually endothermic because it's removing heat from the thermometer, which is lowering the temperature reading on your thermometer. Okay. Questions? Okay. Now, okay. So the first thing I want to do in this next section is definitions of oxidation and reduction. And so what you're really doing is you're comparing these definitions to each other because the definition of it has evolved. And so there are 3 different definitions that you have to know, and you have to be able to differentiate between them. And the IB might ask you to explain or compare why one works and one doesn't work in certain scenarios. And so with this, we will make a table as well. And then in the middle, we'll have the definition in terms of. Okay, so the IB likes to ask their questions and they'll say, explain in terms of why this is an oxidation or reduction reaction. And so that blank after in terms of tells you which definition you should be applying, because if they say electron transfer, then what they're talking about is loss and gain of electrons. So in oxidation, you have a loss of electrons. Whereas in reduction, you have a gain in electrons. Oil rig is the mnemonic device that I usually use to help remember that. Oxidation is loss, reduction is gain. The limitation for this is that you actually have to be able to see the electrons in your reaction to kind of be able to see what's going on. So you might see something like this, or something like, let's say, okay, this, okay. The location of the electrons in your equation tells you whether it's an oxidation or reduction. If the electrons are on the product side, that means you're producing the electrons. That means you're losing them from the system. That's oxidation. If the electrons are on the reactant side, then you're gaining the electrons into the system, so that's reduction. But the limitation, again, is the electrons have to be seen in the equation for you to be able to determine that scenario. So there's a limitation there in some reactions. Okay. the second one is in terms of oxygen and hydrogen, okay? It could be either or depending on what your context is. Usually it's oxygen, but you can talk about it in both senses, okay? Okay. So for oxidation, you have an increase in, oxygen, or a decrease in hydrogen, okay? The increase in oxygen makes a lot of sense because oxygen is very electronegative. So if you bond with more oxygens, the oxygen will pull the electrons away from the other element. So you'll get oxidation. So the ownership of the electrons goes toward the oxygen instead of the other element. And so what you might see is something like this, where the carbon is gaining electrons, so it is oxidizing. And for reduction, it's vice versa. You decrease oxygen, or you increase hydrogen. Let's see. You can see it like in the decomposition of aluminum oxide, okay? And so you're decreasing the amount of oxygens in that species. Yes, Lara? That's a good question. An acid-base reaction, when you're increasing or decreasing hydrogens, let's see. I would say that, how do I do this? I think that's one kind of limitation of this definition, because you could see a change in hydrogen, but you might not see any change in the actual oxidation or reduction by like the transfer of hydrogens in there. So that is a limitation of this definition. And so like that might be something they present. They might say like an acid-base reaction, go state and explain which definition of oxidation reduction isn't applicable here, because you'd say, okay, well, there's an increase in hydrogens, but there's not actually oxidation or reduction occurring here. So this is kind of one of those limitations of that. But when we get into oxidation number, which is the next step, you'll say that the oxidation number of the species in the reaction changes, where in acid base, none of the oxidation numbers change. Yeah. Correct. Yes. Correct. It does not change. That's a good question. So yeah, like when you form a complex ion, the metal ion keeps its oxidation number even when it's bonded with it. Yeah. The last definition, which is the all-encompassing definition, the kind of most most correct definition that always works, is in terms of oxidation number. Okay. So for this, you have an increase in oxidation number. Okay. Something like this, where there's no electrons and there's no oxygen, no hydrogen, those other definitions are limited. But when you actually look at the oxidation number, Fe is 0. In here, Fe is +2. So you've increased in oxidation number. So therefore, iron is oxidizing here. Whereas here, you can talk about a decrease in oxidation number. And you can use the same reaction here because every oxidation reduction reaction has to have one thing that's oxidizing and one thing that's reducing. So here, chlorine is 0, and here chlorine is -1. So it's decreasing. It doesn't have to be a negative number. It just has to decrease, like in terms of a number line. So decrease could be +3 to 0, but it could also be +3 to -3. It could be +2 to +1. As long as you're decreasing in actual value of your species, then that's all that matters. And this is the form that always works. And a lot of y'all, when you're explaining why something oxidizes or reduces, like on the mock exam, it says in terms of oxidation number, and none of y'all, like, and the ones that got it wrong didn't address that actual oxidation number change. So it's not enough to be guessing, oh, I think it's an oxidizing agent or it's a reducing agent. You have to say, well, it's an oxidizing agent because the oxidation number decreases, which means it's reducing. And so, like, and you have to cite the numbers. I would cite the numbers. If they say in terms of oxidation number, I would cite the numbers in your explanation. That's the only way that they'll truly know that you are speaking in terms of oxidation number. So go say that the iron goes from 0 to +2, so it's oxidizing, so therefore must be the reducing agent. That's a full correct answer. Again, we're all about minimizing the points you get off for stuff you actually know, and that you're just not presenting it in the right manner. A lot of these questions where it's either or, they usually don't accept the answer if it's just a guess. You usually have to support it with a rationale to get the 1 mark. Yes, Karen. Yeah, because you're talking about in terms of the carbon gaining oxygens bonded to it. Yeah. So the carbon itself is oxidizing because it's bonding to more oxygens than it did originally. You'll see this in organic a lot. Like, for example, and I'll address this here because I think it is important. Like for SL and HL, you'll see this when you see something like an alcohol going to, oh, sorry, let me make this. Something like this, the oxidation of an alcohol, right? Because that oxidation goes from one oxygen being bonded to carbon to a carbon bonded to one oxygen singly and then double bonded oxygen again. So that's an increase in oxygens there. Whereas for higher level, the reverse, the reduction of that shows an increase in hydrogens or a decrease in oxygens as well. Sorry, a little cut off there, but there's an OH at the end there. So this definition works fairly well with organic structures because you're dealing with oxygens and hydrogens, but there are a lot of issues with this because if there's no oxygen hydrogens, then it doesn't apply, right? And sometimes you'll get a weird thing where one species is gaining hydrogens and oxygens, so then it's really confusing, right? And so there are limitations for these first 2 definitions that are not occurring. So if you want a definition that always works, like it's oxidation number. Oxidation number will always work in every single redox reaction. There is never a situation where it doesn't work. The top 2, there are limitations. Questions about that? Okay. This next table that I'm going to do is period 3 oxides. This seems to be a very popular multiple choice and sometimes short answer question for the IB in relating to like trends and things like that. Instead of ionization energy and stuff like that, they'll just look at period 3 oxides because they do show physical property and chemical property trends. And so when I talk about period 3 oxides, I'm talking about Na2O, MgO, Al2O3, SiO2, P4O10, SO2, SO3, and Cl2O. Now, Cl2O is kind of like there, but you don't really need to know it. And what's nice is these show a lot of good physical properties that are measurable to see kind of their reactions. And so the first thing I want to address is that, let's see, how do I want to do this? We'll do this as pH in water. And let me illustrate it in a slightly different way than I have before. Don't draw this yet, but I'm going to try to show you. Let's see if this actually works visually. I'm not exactly sure if it's going to work. So let me try to see. Okay. This is illustrating pH, okay? And so what I'm trying to say here is this is strongly basic, and this is also basic. This is amphoteric, meaning it can act as an acid or a base. This is slightly acidic, and then acidic all the way across there. Now remember, group 1 metals, oxides are always the most basic because you make strong bases for that. Now MgOH2 is also a fairly strong base, but it's always going to be not as strong as the group 1. Hence the term alkaline earth metals instead of alkali metals. And so there will be a decrease in basicity there, and then it'll become more acidic as you go across. So, but also, that also requires you to know some reactions that are occurring here, okay? You have to know that Na2O plus water produces NaOH. And you have to know that MgO plus water yields MgOH2. And on the other end of the spectrum, you have to know P4O10 plus water yields H3PO4. And that SO2 or SO3 with water forms H2SO4 or H2SO3 respectively. Those are the 4 reactions you need to know for this trend of period 3 oxides. The IB is very explicit about that. Like they literally say in their syllabus progress that, let me read it exactly word for word. Yeah. Construction of equations to explain the pH changes for reactions of Na2O, MgO, P4O10, and the oxides of nitrogen, sulfur, and water. Well, nitrogen oxides, that has to do with acid rain, which we'll talk about probably later on in this week. But those are the main ones that you have to know. So you don't need to know the reactions of Al2O3 and SiO2. But Al2O3 can either act as an acid or a base depending on what it's in, and SiO2 can actually react as slightly an acid in kind of non-aqueous solutions. Okay. Oops, I didn't mean that. Bonding, okay? Differentiating the type of bonding that is occurring here. Okay. Ionic bonding. Okay. SiO2 is giant network covalent. And the rest of them are simple covalent molecules. And when I mean simple, I mean that they exist in individual molecules. Diamond and SiO2 and like graphite, they exist in giant networks of atoms that don't exist as individual molecules. But water is one H2O molecule. Carbon dioxide is one CO2 molecule. So these three over here, or four, exist as independent molecules that are attracted and repelled by each other, not covalently bonded all together in a giant crystalline structure like SiO2 is. And remember, SiO2, even though it's called SiO2, is actually four single bonds to oxygen. Because you would think it's like CO2 because it's the same group, but no, it actually is four single bonds to oxygens, but the ratio is one Si to two O's. Because each O is bonded to two Si's. So you may want to review those structures. Okay. Conductivity. Okay. For your ionic compounds, in its molten and aqueous state, it is conductive. Actually, you know what? I mean, I guess we can just draw it all the way across here. Okay. For your covalent structures, there's no conductivity. Again, because for conductivity, you either need to have free moving electrons or free moving ions. And that's why you require to have molten or aqueous ionic compounds, because ionic compounds in solid form are fixed ions. And so the ions can't move, so electricity cannot move through them. If you dissolve in water, the water also breaks up the ions so that they are freely moving so that electricity can conduct as well. Excuse me. Oh, yes, Erica. Yeah, so this is amphoteric, but it's not amphoteric, so it doesn't produce a acidic solution when you bond with the water. So like these two, like, yeah, they don't behave this way in water, whereas these ones do. So yeah. So Al2O3 is amphoteric, and I chose that word very carefully because amphoteric and amphiprotic are slightly different. Amphiprotic means you can donate or lose, or donate or accept a hydrogen in water. Amphoteric means you can act as an acid or a base, but it doesn't necessarily have to be with water. So like Al2O3 doesn't produce a pH change in water, and SiO2 generally doesn't either. Like if you think about SiO2, SiO2 is quartz, which is sand. So sand doesn't really dissolve in water and doesn't really acidify, but when you put it in with other species, like stronger acids or bases, you'll see that reaction occur. So yeah, that's kind of a tricky one right there. Okay. I'm going to put melting point in here as well. Okay. And this one, I would say relative to the ionic has the highest. And these are fairly low. What happened to my line there? Oh my God. That was really depressing. I just looked at it and I'm like, it's not supposed to be like a stair step. Okay. Yes, melting point. Okay. Oh, because to break the covalent bonds within the network, it's much harder than breaking the ionic attractions between that. So like network things like diamond and SiO2, even graphite have very, very high melting points. Now, I would say that like you're kind of like maybe like splitting hairs with this stuff. So I feel like the question would give you a little more information to separate them. Like they would not just give melting point, but they'd give conductivity as well. Like that multiple choice question, I think there's multiple choice question on one of the practice exams that said like, which is the most probable structure for this? And they give you melting point and conductivity. That helps you kind of eliminate choices for both. So I wouldn't say just melting point, but there should be enough information overall to determine that. Questions about that? Okay. What's the next thing I wanted to go over here?
Mr. Chong, I had one question.
Yeah, shoot.
So, in terms of the melting point for the period 3 oxides, that doesn't only apply to period 3. It can apply to any period, right?
Uh, I would more like to do that with the type of bonding in the way it's related mirror instead of just doing it as a trend across the periodic table.
Oh, okay, got it.
Because there's not really any giant network covalent below SI, and so that gets a little tricky. But so I would relate that melting point to the type of bonding in this example, which is not so much of a trend here, but I was just trying to connect that idea to this.
Okay, all right, thank you.
You're welcome. Okay. Oh yeah, sure. Yeah. So for HL chemistry, this is kind of a big one that I felt was really important, kind of comparing, contrasting, because you won't actually have to like, I don't think you'd have to write in like a paragraph the compare and contrast, but you have to know and be able to identify and recognize it when you're outlining the mechanism for this SN1 versus SN2. So SL, you can take a little bit of a break. I don't know how long it's going to take, so I don't want to like dismiss you, but you can take a kind of mental break right now, SL. Okay. So An SN2 reaction happens mostly with primary halogenoalkanes. Okay. And so in this mechanism, you have something like alkane. Oh, sorry. You have the lone pair of the nucleophile attacking the carbon first. And when this happens, it creates a transition state. Now, because this carbon's not chiral, it doesn't super matter. But if it were a chiral carbon, it would matter. It would invert, like it would be the opposite stereoisomer of the original one. And make sure when you draw the transition state that you draw all of this. The brackets, the charge, the dotted lines for the partial bonds that are occurring. And then you could either draw the bond breaking here, or you can draw it breaking here. But as long as it's going from bond to the chlorine, that's all that matters. And then you end up with this. And the rate law for this reaction is because this is a slow step, it is rate is equal to K times CH3, CH2, Cl, and OH minus. Because there are two species involved in the slow step, the first step. So the rate law will incorporate concentrations of both those species here. And you will want an aprotic solvent, meaning no hydrogen bonding. Because the hydrogen bonding would interfere with the hydroxide's attack on the carbon, because the hydroxide would be more attracted to the solvent than the carbon, because the carbon's only partially negative, whereas the solvent's going to be probably partially positive, whereas the solvent is going to be very strongly partially positive. So it's going to distract the OH from reacting with the C. So you need to have those arrows. You need to have the transition state for full credit in all those manners. It is something you're going to have to memorize. I don't know what to tell you about this. Like, you have to memorize these things. There's no way around that. Okay. Halogenoalkanes. Okay. Tertiary, I should say. Okay. With tertiary halogenoalkanes, the reaction happens a slightly different form because the nucleophile can't access the carbon because the CH3s are kind of blocking it. So it has to wait for the Cl to break off first. I guess we don't really draw brackets here. We can just write like that. And then the hydroxide attacks the carbon. So this is a carbocation. So transition state versus the formation of a carbocation. But you still end up getting the alcohol. Wait, sorry, say again, Erica? So the secondary can do either one. So That's a good question. So secondary halogen alkanes can do either one, and oftentimes in the test, they'll allow you to do either one. If they specify, obviously you have to do a certain one, but for secondary, they would accept either mechanism. So just draw whichever one you feel more confident about. Now here, because this is your slow step, the rate only depends on your halogenoalkane, because the hydroxide is not involved in your slow step. It has to wait for the carbon to break its bond and then allow the carbocation to form, then react with the OH, which is why you're allowed a protic solvent. Because the hydrogen bonding helps stabilize, the carbocation. So the protic solvent, like water, will surround the carbocation and stabilize it until the OH breaks through and creates that bond with that carbon. And it also kind of makes it easier for the Cl to break off as well. And don't forget, I guess I should say this as well. I forgot to say this, but this is SN2, which is called substitution nucleophilic bimolecular. Because there are two molecules that are involved in your slow step. And this, SN1, is substitution of nucleophilic unimolecular. Yes, Alexander.
So one doesn't. Why doesn't SN1 have H?
Wait, I'm sorry, say it again.
Why doesn't the molecule that you drew spoke a little bit off right? Why doesn't that have H?
It does. But we're talking about the solvent here, not the actual chemicals. Yeah, sorry. The alcohol is going to have hydrogen bonding, Alexander. We're talking about the solvent in which this reaction occurs in. We don't want hydrogen bonding for this because it'll interfere with the OH's attraction with the carbon. Whereas here it doesn't matter because once the carbocation, it's already going to be a stronger attraction than the water or whatever hydrogen bonding is. So it'll still go there and won't affect the reaction. Good clarification question. Wait. For SN2? It'll interfere with the hydroxide's attraction for the slightly positively charged carbon. Man, I really hope this mechanism is on a test. I know y'all might not, but I feel like we've done it so many times that hopefully it's second nature by the time the test comes around on Friday. And all these arrows are important, and those intermediates are important as well. One of the terms that I don't know if we said a lot is they'll say in a concerted step. Is that the right term? Let me make sure I say it right. Yeah, a concerted reaction. Okay, that means it all happens in one step. It's just that the transition state is what we suggest must theoretically happen in the middle of this process for the reaction to occur. So remember, transition states don't always, like, you can never stop the reaction at the transition state, but they have to exist for it to occur. And so all the experimental evidence shows that the hydroxide has to attack from the opposite side from the chlorine to break the bond off, because all the products produce that certain orientation. Yes, Erica? They would say, outline the mechanism of the reaction between chloroethane and sodium hydroxide. So chloroethane, you draw it, you say, okay, that's a primary halogen alkane. Sodium hydroxide has hydroxide, so that has to be a nucleophilic substitution. So then that kind of gets the ball rolling for that. I think that's how they asked it on your mock exam as well. They'll say, like, outline the mechanism of the reaction between chloroethane and sodium hydroxide using curly arrow, like using arrows, and include any transition states and stuff like that. Okay. One last thing. Oops. What was I going to look at? I lost my train of thought here. Oh, yeah. Last thing for high level, and we're actually going to call it a day. So, factors that affect rate. So there are three kind of major factors that affect rate. Okay. Actually, there's really mainly two. Okay. The leaving group, which is the halogen. Okay. I leaves faster than bromine, leaves faster than chlorine, leaves faster than fluorine because of the weaker bond. The degree of carbon. Okay. So tertiary reacts faster than secondary, reacts faster than primary, which reacts faster than, like, the methyl group. I'll just write this. Now, this is the one that gets priority. So when you're trying to figure out which halogenoalkane reacts the fastest, you go by degree of carbon first. So a tertiary, no matter what type of leaving group you have, always reacts faster than a primary. And then if you have two tertiaries, then you look at the leaving group to differentiate between that. Oh, okay, there's technically one more thing. Happens faster. Yes, so the less than symbols are for the speed of the reaction here. Technically, the nucleophile also matters. So OH is better than H2O because of its negative charge. But for our purposes, we're only dealing with OH nucleophiles in our reaction. So that one isn't really as a matter of fact. It's these two that really matter in your factors that affect those reactions. Yes, Lara. Okay, let me add a word in there. Tertiary carbocations are the most stable. So, like, it's the fact is that tertiary carbocations are the most stable, so they're the most reactive because they can most easily lose the halogen because they're stable without it. Yeah, so you have to be really careful. Yeah, tertiary carbocations are the most stable, which is why the reaction rate of the substitution is the fastest, because it can form a carbocation the most easily, which then allows the nucleophile to react. That's a good question. Okay. That's the end of today's lesson for compare and contrast. There's a lot of other stuff that you can do compare and contrast, but these are the main things that I wanted to highlight in here. So if you're on Zoom or watching on YouTube, hopefully it was informational, and the document is in my Dropbox for the class, and I will sync it up right now. All right, have a good day, y'all.